Apparently, this video needs to start in a math class. So, you're sitting in a math class and you're hoping they would talk about something more interesting than cubics, because who actually needs to know about a curved straight line with a squiggly bit in the middle? If you were allowed to have music playing, you would absolutely be trying to open Spotify right now, but you're not, because you're a good student. So, you just wait for your brain to think of a piece and it kind of pops into your head. And as your math teacher is desperately begging the class to pay attention because math can be found everywhere, you realize math can be found everywhere. Math obviously can be found in all forms of music, but especially this one, because it's a Vocaloid song. I'm not going to try and play the actual song because of copyright reasons, but I think this piano cover is close enough. Anyways, Vocaloid and math. All the way back in 2000, people wanted to create synthetic voices. This was before the age of generative AI such as diffusion or adversarial neural networks, both of which have a lot of math that I would love to talk about, but that's completely out of the scope of this video. Without the cool AI stuff of the modern day, people would use a voice bank, a collection of recordings of all possible sounds a human can make, and then squishing them together to try and create words and sentences and verses. Based on the research that was conducted then, Yamaha, because they do everything related to sound, released Vocaloid as a commercial product in 2004. They figured out a way to blend different sounds together by closely aligning the pitches of each sound, basically autotune, and then extended this feature to allow users to change the pitch of different parts of the Vocaloid speech, allowing a computer, for the first time, to sing in human language. The cultural impacts of Vocaloid are also well out of the scope of this video, but there are many. The thing that's really interesting here is the autotune, because math. In essence, to change the pitch of a pure tone, like this, you need to increase the frequency of the sound. You can do this by squishing the wave, but it's a little bit short now, so you can fill in the blanks so that it matches the original length. This works great for these simple sounds, but what happens when you have a signal that looks like this? Once you squish that, how do you work out how to extend the duration? The secret is that you've done it wrong, so let's go back to the start. All of these crazy sounds can actually be broken up into several frequencies that add together. And would you look at that, you're back to thinking about squiggly lines. Different squiggly lines, but still squiggly lines nonetheless. And for some reason, to tell how much of a signal a wave makes up, you can multiply the signal by the wave and look at the area under the curve, an integral. Like, for this specific signal, multiplying f of x by sine of x gives us a reasonably large integral, and multiplying f of x by something like sine half x, which isn't in the signal, gives us a negative integral, which, at least according to this brute force oversimplification, is weird, but is sort of a fact that we have to accept in magical math land. And we can kind of graph this. It gives us some spikes where the frequencies are. And now you know the frequencies, you can squish the individual frequencies, add some more to end and put them together, and it should sound roughly alright. As for why the real Fourier transform formula looks like this, it's because there are very neat mathematical ways to write sine and cosine functions, see Euler's identity for further reading, as well as a very convenient way to write that you are trying every possible frequency. Computers are allowed to take a couple of shortcuts by not trying every possible frequency and only looking at small lengths of time, as well as using other algorithms like the fast Fourier transform, which is completely out of the scope of this video. Outside of music, the Fourier transform is used to break Wi-Fi signals down into separate frequencies, meaning that everyone can communicate through the air without being impacted by interference, at least in an ideal world. It can also detect vibrations in the ground, such as earthquakes, by filtering out unnecessary frequencies and looking at a few important ones. In a similar fashion, it was used to detect underground nuclear testing back in the Cold War. People say that it prevented total nuclear annihilation, but I would be careful to make such a bold claim. Okay, cool. You're not an internet-connected device or a geoscientist or a military strategist, but what you are is a human, and your ear does a Fourier transform, sort of, by exploiting some cool physical properties that allow nerves to respond to specific frequencies, making it super easy to tune out whatever your math teacher was saying about those curved straight lines with squiggly bits in the middle.